Hello, my name is Florian, and today I will give you an introduction to our newest model, the LMG671, and use it to perform efficiency measurements on DC power supplies. The LMG671 is an improved redesign of the already successful LMG670. It's fully form, fit, and function compatible with its predecessor and incorporates upgraded hardware and features. The size of the touch display has been increased by more than 33% to provide even better usability and readability. With more internal memory, you can now record transients of up to 16 million samples per track. USB 3 allows for increased transfer speed. So let's take a look at today's measurement application, DC power supplies. Every electronic device that draws its power from the electrical grid is connected to it through a DC power supply. The majority of them is meant to deliver power in the form of 5 or 12 volts with regulated or unregulated current. It is not an exaggeration to say that every household nowadays contains more or less a dozen power supplies. Your laptop uses one, your wireless router as well. Your TV has one built inside it. Battery chargers and UPSs are also entirely or partially power supply units. Much more sophisticated power supplies are commonly used as laboratory equipment. Considering that the number of DC power supplies around the world can be easily estimated to billions, it is of crucial importance that the energy waste that they contribute to is minimal, and the harmonic pollution that they inject into the grid voltage is strictly limited. Let's start with a linear laboratory power supply with which we will feed a high power resistor with 800 milliamps of current and study the measurement. Here it helps organizing the channels into groups, so we will use group 1 for the AC input and group 2 for the DC output. We can either control the LMG directly using the touchscreen or on a PC using the LMG remote software. This way we can apply different settings on each group that are relevant to each measurement. The default measurement menu on the LMG671 will give us an overview of the voltage, current and power. On the output, by observing the AC and DC components of the current and power, we see that our power supply provides a pretty steady DC output with minimal ripple. The power factor is equal to 1, which is expected due to the ohmic load. Looking at the waveform in the scope graph, they also look pretty stable. In the plot graph, we see a presentation of the cycle values over time, in this case, the DC voltage and current. Here we can observe the measurement equipment's long-term behavior. On the input, first thing to notice is that the line current drawn from the grid by the power supply is heavily distorted. In the frequency spectrum of the line current, we see a strong presence of both odd and even harmonics, with the 3rd, 5th, 7th and 11th order being the most dominant. The vector graph helps us see that the current's first harmonic is lagging the voltage by about 26 degrees. Both distortion and displacement lead to an inductive power factor of around 0.74. If we further analyze the harmonics of the power, we can separate the reactive power to the part caused by the lagging current and the distortion power. In the power menu, we can also find the efficiency tab, which uses the group concept to calculate the efficiency. Here we measure an efficiency of only 12.8%. Our lab power supply seems quite inefficient. Integrating the power and current over time will give us the energy and charge that the load consumes. That's exactly what the energy menu does. The integration can start and stop either manually or by applying an external signal. It all comes together in the custom section of the LMG SKUI. We always encourage the users to build their own menus and write scripts. The result is a single screen overview of the entirety of the measurements. Here we have done the same, a collection of all the important values together with a plot of the voltage and power, an indicator of the load presence, and calculations of further interesting parameters using the script editor. Now let's try something else. We will connect a smartphone charger as DC power supply and use a smartphone as load. The wiring is identical. Despite its significantly smaller size, the charger delivers more or less the same power as the lab power supply. So let us check their differences. The smartphone charger is a switching power supply, and although its general purpose is the same, the way it operates is much different. We can observe these differences using the LMG671. All we have to do is connect the charger in the place of the lab power supply using this breakout box to access the current and voltage on the DC side. The same menu we used until now works perfectly for this measurement too. First thing we notice is that the efficiency of the switching power supply is much higher. But what is more interesting to observe is the current on the input. It looks much different. In fact, it resembles a spike. a typical line current of a switching power supply that is closely related to its operation. Here, a Fourier transformation will give us a better picture of the harmonic pollution that the charger introduces to the grid. We immediately notice the absence of even harmonics and the wider spectrum. The total harmonic distortion of the current is almost 3 times higher compared to the linear power supply. To ensure good electromagnetic compatibility, this influence on the grid current must be controlled. There is an entire family of IEC standards that dictate methods of measuring harmonics and the limits of current harmonic emissions that different categories of devices shall comply with. By measuring harmonics according to the IEC 61004-7 standard and using the LMG test suite, we can test the charger according to the limits of the IEC 61003-2 standard and prove its compliance. Another basic difference with the previous measurement on the linear power supply and resistive load is that now we are providing power to an electronic load. The DC current and voltage are controlled by the battery electronics. The plot graph helps observing the different load behaviors during different stages of the battery's charge cycle. All in all, we have shown 2 applications of DC power supplies with the same principle but quite different executions. The LMG671 helped us study and compare the power quality and efficiency of both setups at the same time. For the accuracy of the results, we rely on the LMG671's high precision while using its customizability to simplify our tests. For more information about the LMG671, feel free to check our website and the technical brochure in the description. Thank you for watching.